Similar to the electric field, the magnetic field is a map of how a magnetic material influences the space surrounding it. In specific, how a magnetic particle will respond. Since magnetic materials must have both a north and a south pole, magnetic field lines have no start and stop points like electric field lines do. Instead, they are continuous loops that surround the source of the magnetic field. Like the electric field, the magnetic field at any point has to be both specified by a magnitude and a direction, meaning how strong is the field and in which direction will it push a test charge. Remember, we say that the E field and the B field are therefore vector quantities. When electrons move, or when current flows, which is just the movement of electrons, a magnetic field is generated around the current flow. And this is the basis for the device known as the electromagnet. The magnetic field in this case is oriented in concentric circles around the current flow, and its strength decreases inversely with the distance from the current flow. So here you have to imagine we've got some sort of wire. Right here, there is current flowing in this direction. What happens then is a magnetic field surrounds the current carrying wire in these concentric circles. If I want to know the strength of the magnetic field at any distance, radial distance r away from the wire, the strength of the magnetic field is dependent on the current, it's dependent on the radial distance away, and it's also dependent on the ability of the space around the wire to support a magnetic field. We say that B, the magnetic field strength, is equal to the magnetic permeability of free space times I over 2 pi r, and this is measured in units of Tesla. So different materials can support different magnetic field strengths, and so we will indicate that this is again for a vacuum. And in general, the ability of a current carrying wire to produce an electric field or a magnetic field at some distance is going to be B, just mu, times I over 2 pi r, where mu is equal to mu 0 mu r. And this equation here accounts for the effect of a material. And so what is this? Well, as I just said, mu is called magnetic permeability. Again, think of it as the ability of a material to support or sustain a magnetic field. We've got mu 0, this is the permeability of free space. It's a universal constant, like gravity or something like that. It's 4 pi times 10 to the minus 7th henries per meter. And then finally we've got the relative permittivity mu r, and that has to do with the materials. Relative permeability. Non-magnetic materials, copper, things like that, they've got a relative permeability around 1. Appendix E of your text lists a whole slew of these magnetic permeabilities. Magnetic materials, things that concentrate lines of magnetic field like iron and steel and things like that, they're going to have magnetic relative permeabilities much, much greater than 1. 10, 100, 1,000, 100,000, depending on the magnetic ability of the material. And so you may look at that and say, henries per meter, I wonder if that in some way is related to the inductor. And indeed it is. An inductor is a device that uses the magnetic field to store energy in a coil of wire. So the simplest conductor consists of a coil of wire made of N turns with a total length of L meters wrapped around some sort of coil. This coil, or some sort of core, excuse me. This core is some sort of magnetic material with high relative magnetic permeability, and it's placed inside the coil to increase the flux density. In this configuration, when we connect this coil to a current source, current is going to flow and a magnetic field gets established. We can relate current, the inductance of the device, and the charge with the following equations. We've got the inductance L is equal to the magnetic permeability of the material times the number of turns squared times A. A would be kind of the cross-sectional area of this coil, and then we divide that by L, which is just, as indicated here, it's length. So we've got magnetic permeability mu, again, times N squared over A divided by L. And the total energy, that just gives us the inductance, the total energy is therefore equal to E equals 1/2 Li squared. So it's very similar to the capacitor, which was 1/2 CV squared. So the energy stored in a inductor is related to magnetic field, and therefore the current. Energy stored in a capacitor is related to the electric field, and therefore the voltage. So intrinsically, the electric field and the magnetic field are linked, and this is described by Maxwell's equations, but to prove it to you, what I want to do is end today's lecture with a simple thought experiment. So let's consider a beam of charged particles that are moving at a constant velocity. So we've got these charged particles, electrons or something like that, and they're moving left to right at a constant velocity. So I've got E, 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 E. These things are all moving left to right at a propagation velocity of mu sub p. Now, let's take a small slice of that beam, just a small slice of it. The E field, due to the section of the beam, is just determined by the total charge contained in that section. E in here is going to be Q over 4 pi epsilon r squared. So the E field at some distance, here, is going to be Q over 4 pi epsilon squared. The magnetic field instead depends on the rate of charge flow through the section. The magnetic field is B at some distance is equal to mu I over 2 pi r. So there's an important difference here. Electric field dependent on total charge here. Magnetic field dependent on rate of charge flow, or charge per unit time. For example, a few charges moving fast can deliver the same current as many charges moving slowly. In such a case, the induced magnetic field will be the same, but the E field will be different as it depends on total Q. So if I've got some representative area and I've got a couple charges moving through it really, really slowly, but then I've got one charge moving through it super fast, that's the same amount of current. It's charge per second. Current is. But total charge is the sum of those three in the case on the top, where total charge would be just one charge unit in the bottom. So Q is different, but I's the same. So we see that in that situation, the electric field and the magnetic field are different. What we'll see later is that if the current associated with this beam of moving charged particles varies with time, if I changes, meaning that the change present in a cross-section of the beam also varies with time, then the electric and the magnetic field become coupled. In fact, a time-varying electric field will always generate a time-varying magnetic field, and a time-varying magnetic field will always generate a time-varying electric field. The rate at which the lines of these fields travel through space or through material is the propagation velocity that was introduced earlier in the video. And this relationship between propagation velocity, magnetic permeability, and electric permittivity can be quantified with the relationship mu sub p is equal to 1 over the square root of magnetic permeability times the electric permittivity, which sometimes is written as mu 0, not epsilon, mu relative times E0, E relative. And in a vacuum, that's mu sub p is equal to 1 over the square root of mu 0 times 1, epsilon 0 times 1 is equal to 1 over the square root of mu 0 and epsilon 0. And if you plug in those two constants, what you'll find is that that's the speed of light. So the speed of light is fundamentally governed by the ability of an electric field and a magnetic field to permeate a vacuum, and that's governed by magnetic permeability of free space and the electric permittivity of free space. So that's the end of the introduction to electromagnetic fields. Hopefully you get a good introduction to that, a good feel for it. And next lecture, what we're going to do is we're going to start describing electromagnetic fields mathematically, a little more mathematical rigor.